Okay, just a little review. Last time we talked about 1.6, which straightforward type of continuity, trig functions, exponential functions, and inverse functions. So we talked about you would be expected to be able to evaluate sine, cosine, tangent at the basic angles. Pi over 4, pi over 3, pi over 6, pi over 2, or any multiple of those. 5 pi over 4, 3 pi over 2, things like that. So you understand what quadrant it's in and how to verify that. Most of your scientific calculators can do that as well. So convince yourself you're in the right mode. So if you plug in sine of pi over 2 and you don't necessarily convince yourself you know exactly what that is, your calculator should be able to do that. Granted, you're in radians. If you plug in sine of 90 and you're in radians, it's going to give you a number that doesn't make sense. So at this point, you should be able to hint, okay, something's not right in my calculator. It should be something I might understand. You will also have to enter like exact answers. So if it was like 1 over square root of 2, your calculator might not tell you that. So just be aware of that. We talked about the exponential functions where they're continuous on. So if a function is continuous, you have to verify there's no problems on your domain. So continuous on the domain, we did this example. Tangent inverse was continuous everywhere. If you look at the graph, there's no problems for tangent inverse. The natural log function, you can only input positive numbers. You cannot even input 0. So since we're inputting numbers that come from tangent inverse of x must be positive, so our problems occur when it's negative, which occurs from minus infinity to 0. Then our denominator had problems at plus or minus 3. So once we figured out where all of our problems were, we could verify the function is continuous everywhere else. We spent some time looking at the proof of the squeeze theorem in the book for the limit sine of x over x as x goes to 0. That equals 1. Now you can take that to be true. So you don't have to ever prove it again. You can know that if you take x to go to 0 of sine of x over x, that approaches 1. So we spent some time on showing the next limit that now you can just use, that the limit as x goes to 0 of 1 minus cosine of x over x, that approaches 0. The reason why is we use the sine of x over x here goes to 1, and then we have 0 over 2, so we know that goes to 0. So this can be used in the proof of this. But we ran out of time to look at too many examples, but the first example we did was sine of 3x over sine of 5x. We simplified this to get this into the exact form we know how to deal with, and we get the answer as 3 over 5. So in general, sine of something x over something x equals 1. You need to get it in this form to conclude that by using the squeeze theorem, which you don't have to prove. Does that make sense? Question?
Yeah, I just doing some of the homework
Mm-hmm.
I felt like I could just kind of figure out what the answer was and just know it. So I know you said on some of them you want to see the work, but
Yeah, on Wiley in this section 1.6, a lot of them you kind of know why, but convince yourself. Like this one, we did an example. What do we think the answer is here? 17 over 2 is the correct answer, but you would need to convince yourself you could show that. So let's look at this example. So this is number 27, 1.6. So today is the 5th. 1.6, number 27 on Wiley. We have the limit as x goes to 0 of tangent of 17x over sine of 2x. So if you guess 17 over 2, you'd be correct, but on an exam, on the final exam, on quizzes, you need to show why the answer is 17 over 2. So I could rewrite this. I really want to get sine of something over something x, right? So what would be the best approach here for tangent? If I plug in 0, tangent of 0 is 0, and sine of 0 is 0. So I have 0 over 0, so I can't evaluate it. So I need to get it in a form that I can evaluate. Very good. So I can write this as sine of 17x over cosine of 17x divided by sine of 2x. So what would I need to do, and maybe if I write it as the limit as x goes to 0 of 1 over cosine of 17x, sine of 17x divided by sine of 2x. Kind of looking at, what would I need to do to this sine of 17x to get it into something I know how to evaluate? Very good. So if I 17x over 17x, that doesn't change my numerator. I only multiplied by 1. But I picked my 1 to be 17x over 17x because I know that the limit as x goes to 0 of this is going to turn to 1. So it's going to simplify my expression. What am I going to do to the denominator? Divide by 2x. So I have a 2x up here and a 2x top and bottom by 2x. So this expression here is also going to go to 1. I can use the squeeze theorem. I don't have to prove anything. I know that to be true. So I have the limit as x goes to 0. I'm left with a 17x divided by cosine of 17x divided by 2x. Right?
The squeeze theorem, is that what you did there?
Yes. Sine of something x divided by something x as x goes to 0 always goes to 1. And I know that from the squeeze theorem. It turns out I could prove the tangent of 17x over the sine of 2x goes to 17 over 2. That's what I'm doing. I'm showing that's true. Because if you just guess 17 over 2, you don't know why that is. Why is it 17 over 2? We proved the squeeze theorem that the sine of x divided by x goes to 1 by taking the area of the smaller triangle, the area of the sector, and the area of the larger triangle, and using the squeeze theorem to show that. So you don't have to do that every time. You don't have to do that again. So you want to manipulate anything else to be in that form to apply that doesn't go to 0, it goes to 1. This goes to 1, and this goes to 1. Question?
Can you go back up to the stuff yesterday with the 1 plus tangent squared?
That example? This one?
Yeah, I don't remember doing it.
You don't remember doing 1 minus cosine x over x?
No, it was, I think it's the other page. Or maybe no, just kidding.
With
But it was,
down some? This one? With tangent? This is tangent 17x
so
over
I
2x.
guess we just didn't do the trig identities.
The trig identities here?
Yeah, we didn't do
Oh, did we do this in your guys' class? Is this not your guys' notes? It might have been the other section's notes. Did we do this? Did we do this mini? Okay, I probably just switched one of the pages. So did we use this limit to show this? No? Okay. So after I do this example, I'll finish with that. So I apologize for that. I must have grabbed that from the other section. Okay, so at this point, I want to get a fraction, a complete fraction. A fraction over a fraction, I want to flip and multiply, right? So if I do that, I end up with the limit as x goes to 0. On top, I have 17x. On 2x over 1, if I flip that and multiply, I end up with cosine of 17x times 2x. Right? I have a true fraction now. So the x's cancel. And I'm left with the limit as x goes to 0 of 17 over cosine of 17x times 2. So on top goes to 17. What's cosine of 0? 1. So this goes to 1, and this goes to 2. So my answer is 17 over 2. So this would be showing your work.
I know a lot of times, especially when it concerns math, the tests are really like time sensitive, like you've got to really hurry.
Yeah.
Like this seems like a really time consuming kind
It takes some time.
to prove a really easy.
But how do you know it's 17 over 2? Because you did this, right? So now if I give you the limit as x goes to 0, 17 of 25x over sine of 5x, you know the answer is 25 over 5. The reason why is this work. So a lot of time,
Work that way whenever it's tangent on top.
it will.
Okay.
And this is why, right? I could do a proof and say the limit as x goes to 0 of tangent of ax over bx, and I want to show this is going to be a over b, and prove that. But the way I would prove it would be doing all this work, and then I can make that conclusion. So yeah, on the exam, I try to write them to be well within the 50-minute mark. So a lot of this stuff, I wouldn't necessarily. If I did put this one on there, it would be very important to show your work there. And I would say work is very important. There's a statement about, an unsupported answer is not worth anything. It's very important to say, okay, this is where I started, and this is the answer. This is why this is the answer. Question?
You just wrote tangent ax over bx. Does it not matter that it's sine on the denominator?
It should be sine of bx, yeah. So this is sine of bx. I think it would still be a over b. Yeah, so I could go through this and prove this in general for a over b. That's the answer. And this could be a good exercise on the exam without numbers and to show, okay, I can write tangent of ax as sine of ax over cosine of ax. Pull that out, then I need to multiply top and bottom by a, and I need to multiply top and bottom of my denominator by b, go through, and then I would get everything to cancel except a over b. So showing your work's important. Now on Wiley, you can say, okay, I've seen the answer, I can kind of fit it into after that third time, but you really need to make sure that if you did need to sit down and write this out, you could do it, and you know why. The 17x over 17x as x approaches 0 goes to 1. Because the squeeze theorem. Question?
So if we just did the proof, would we have to show the work to all of them, or can we just write the proof and then just start writing the answer?
Yeah, if I give you 15 of these and you did the proof, then you could just write the answer. But I'm not going to do that.
Okay.
I give you one
Okay.
and tell you, show this or prove this. I might say that equals 17 over 2, prove it. Every semester on the final, there's problems like that, where they give you the answer. The answer's not worth anything. It's the proof of the answer. Can you show why this equals 17 over 2? Question?
Can you do an example where you use the 1 minus cosine?
Yeah, I'm gonna show that equals 0, and then do an example of where that would come in. Okay, so the next theorem, or the next limit your book shows is the limit as x goes to 0 of 1 minus cosine of x over x. It turns out this equals 0. But why does it equal 0? Well, let's go through the work. So if I was to evaluate this, if I plug in 0, cosine of 0 is 1, so I have 1 minus 1 over 0. 0 over 0. So I need a place to start. I have to cancel the 0 in the denominator because it's making my life miserable. I can't evaluate it. So where would be a good place to start on this problem? Yeah, well, the numerator, right? Maybe, because a lot of times when we have something, we multiply top and bottom by like the conjugate, which it's not really conjugate, it's not imaginary number, but if I multiply top and bottom by 1 plus cosine of x, it might get me somewhere. So let's approach that. So if I do 1 plus cosine of x, 1 plus cosine of x, I end up with the limit as x goes to 0 of 1 minus cosine squared x. So at this point, it didn't get me too far, but in trig, never fail, you can always change your expression by using an identity. So if you recall the trig identities, you only need the first one here, but let's write them out. So the trig identities, I have sine squared x plus cosine squared x. equals 1. You guys remember that one? The Pythagorean trig identity, sine squared x plus cosine squared equals 1. That's the only one you really have to memorize. The other two you can get from this one. So if I divide by sine squared, this whole expression by sine squared, I'm left with 1 plus cotangent squared x equals cosecant squared x, right? 1 cosine over sine is cotangent, and 1 over sine is cosecant. So I got that second identity by just dividing by sine. Now if I divide by cosine from the top one, sine over cosine's tangent, so I have tangent squared x plus 1 equals secant squared x. So if you memorize that first one, you get the other two for free.
How'd you get the third one?
I divided this top one by cosine, right? Sine over cosine's tangent, cosine over cosine's 1, 1 over cosine secant. So you get those for free. So if you notice, I can rewrite this as sine squared x, which is good because if I have sine of x over x, I know that goes to 1. And this x is giving me some problems. So if I can get something in the form of sine of x over x, I can circle that, say that goes to 1, and then deal with what I have left. So I have the limit as x goes to 0 of sine of x times sine of x, there's a reason why I write it like this, divided by x times 1 plus cosine of x. So now, if I take one of the sines and divide it by x, I know this goes to 1 by using that property we learned from the squeeze theorem, right? So this goes to 1. So I really have the limit as x goes to 0 of 1 times sine of x over 1 plus cosine of x. What's sine of 0? 0. What's 1 plus cosine of 0? 2, because cosine of 0 is 1. So I have 1 plus 1, 0 over 2. What is 0 over 2? 0. 0 over 2, perfectly fine. 2 over 0, you got a problem. So it turns out now you can use that the limit as x goes to 0 of 1 minus cosine of x over x equals 0. In any problem you might come across, you could use this. If I ask you to prove this, you need to do this kind of work. You see an example where this might come up, 1.6. Okay, so let's look at number 32 in your book. So number 32, we get the limit as h goes to 0, sine of h over 1 minus cosine of h. 1.6. So what would I like to do to the numerator to make my life easier? Because if I plug in 0, I have 0 over 0. Huh? I could go about that, but I know that 1 minus cosine of h over h as h goes to 0 goes to 0. Rationalizing the denominator, if I do h, okay, so do I want to go about? I want to use the properties that I already know. I could go about rationalizing the denominator. So we're going to come up with the same concept. So here, if I divide by h on top, and I divide by h on bottom, it's the same thing, right? H over h, the h is going to cancel. This I know goes to 1, right? This I know goes to 0. 1 over something going to 0, the limit does not exist. So if you rationalize the numerator, you could do a lot of trig and still come to the same conclusion.
How's the
because we just shown that the limit as x goes to 0, 1 minus cosine of x over x goes to 0. You could have something very similar. I don't know if they have.
So this one, you can just write doesn't exist,
Yes.
even though the value was not supposed to say the value 0 on the problem.
If you have 0 over 0, you don't know what's going on. 1 over 0, you know it's not going to exist. But 0 over 0, you have issues. Does that make sense?
Yep.
I don't know if I stressed that as much. Yeah, a constant over 0, you have problems. If it's a constant over something going to 0, then you have to evaluate the right side limit and the left side limit. They might both be minus infinity type thing. If you're a right side limit, you're always going to be able to put plus infinity, minus infinity, or doesn't exist if there's oscillation.
And the differentiation on those types of problems for this one is that it would have a plus or a minus after the 0.
Yes, yes. If the right side or the left side, yeah.
Okay.
Which you would have to then, if I look at this example here, if I take 0 on the left, if you think of 0 on the left, this is still going to 0, and this is still going to a constant. So 0 on the left goes to 0, 0 on the right goes to 0, which has to be true because we know this function is continuous. And so that means that the limit on the right and the left has to exist and equal the limit at that point. Yes. Okay.
On that example you just did,
Yeah.
I can see how you illustrated that proof by dividing by h, but isn't it just as intuitive to know that the sine goes to 0 is going to be 1, and 1 minus cosine of h goes to 0 would be 1 minus 1?
Yeah, that's 0 over 0. Oh, yeah, I guess you could. Yeah, you could say, yeah, 1 over 0. Definitely so. You could put that 1 over 0.
Okay.
I just pulled this example up to see what might come up. Here, if we look at number 36, I think it might be more useful in the case. If I have 36, h goes to 0, 1 minus cosine of 3h divided by cosine squared of 5h, sorry, 5h minus 1. So if I plug in 0, I get 0 over 0. I have problems. So I need to be able to simplify this. And this might not, this might take you a little bit more time, but I want to continue on to 2.1. So I'm just going to go through what would we do here. Take the limit as h goes to 0. On top, 1 minus cosine of 3h. On bottom, this is actually a difference of squares. It might not be as easily seen, but this would be cosine of 5h minus 1 times cosine of 5h plus 1.
Is the square affecting the factor?
Huh?
The square on the cosine, is it affecting the 5h?
No, it's cosine squared. Cosine of 5h squared. You could write this as cosine of 5h quantity squared. Generally, it's written as cosine squared of 5h. You take cosine of 5h and then square it. So see where I want to go with this. So I'm not for sure. We will look at this one tomorrow. That would be 2, 6, 13. So we'll come back to this one. And I want to continue on with 2.1. 2.1 has to do with tangent lines and rates of change. Eventually, we're going to get to the definition of the derivative. So 2.1. Lines and rates of change. two concepts you talk about in this chapter: average rate of change and instantaneous rate of change. You can be talking about the average velocity, instantaneous velocity, various different types of applications. In college algebra, you did find the slope between 2 points, and that was the average rate of change. So if I take these 2 points and I name it P and Q, I'm going to name P x naught comma f of x naught, and I'm going to name Q x comma f of x. So I have this point x, and I have this point x naught. This distance between these two would be x minus x naught. I'm going to name that h for a next example. So if I look at the slope between these 2 points, this is called a secant line. Let's see. And that's going to be your average rate of change. So to calculate the slope of your secant line, you're going to take f of x minus f of x naught over x minus x naught, right? This is basically change in y over change in x. So if I ask you for the average rate of change between point A and point B, that's f of b minus f of a over b minus a. You guys have done that a lot, right? Where the calculus comes on is the instantaneous rate of change. So at one instant in time, what's the rate of change? And that's known as the equation of the tangent line. So let's see if I get it. If I look at point P here, so this would be the tangent line.
That always starts from 0.
No, it's tangent line is touching the point of the graph at one point and going away. So the tangent line at Q would look like this. So let's say this Q kind of comes like this. So this is the function. Then the tangent line at Q would look like this. Do you see that? So if you took a ruler and the ruler could only touch the graph at one point, these would all be tangent lines. Does that make sense? So tangent line, at Q, and this would be the tangent line at P. So there's kind of a lot going on in this graph, right? Do you understand the difference between the average rate of change and the instantaneous rate of change? So instantaneous rate of change instantaneous is where the calculus comes in. And so that's going to be the slope of the tangent line. The slope of the tangent line is going to be the limit. So let's see the slope of the tangent line at P. The limit as x approaches x naught of f of x naught. Let's see, f of x. I want to use the same notation your book uses. So they use f of x. Sorry, here. This is f of x minus f of x naught over x minus x naught. Okay. Very, very similar, right? The same difference quotient, except now we're taking the limit as x approaches x naught. So,
Is that first one just an f of x?
yeah, it's just an f of x. Sorry. I really need to bring white out here, maybe. Okay, so do you see the difference? Slope of the secant line, you plug in your change in y over your change in x, you get a value. That's your average rate of change. Your instantaneous rate of change, you're going to have to apply the limit. And your book first approaches this as if this x value is approaching x naught. So x is approaching x naught, meaning this distance is going to 0. So if I plug in f of x minus f of x naught over x minus x naught, I'm going to get another value. That value is going to represent the slope at that point, at point P, where your average rate of change represents the slope between 2 points. There's no calculus in average rate of change. Instantaneous rate of change, the only part of calculus here is this limit. Right? So your book gives an alternate expression for this. I'm going to draw another graph down here. So an alternate expression before we get into too many examples. Alternate expression. And they say, let's call h x minus x naught. So if I have, this is x naught and this is x, and I have some function, then this distance here would be h. So I want to take the limit as h goes to 0. So this would be, I could rename the point x, and this point would be x plus h. So do you guys see that? So it's just naming them something different. So this would be f of x plus h minus f of x over h, right? The change in y over change in x. This point here would be f of x plus h. Sorry, it would be x plus h comma f of x plus h. This would be x comma f of x. Change in y over the change in x, right? X plus h minus x would be h. So exact same concept, different notation. So if I call this point x and I add h, but h is going to 0. So if I add some small distance to x, I have x plus h. Right? So if I put in f of x plus h, I get it out. If I put in x plus h, I get out f of x plus h. That's my y component. If I put in x, I get out f of x. So then my setup here is my change in y, which would be f of x plus h minus f of x, over my change in x, which would be x plus h minus x, which would just be h, right? And I take the limit as h goes to 0. This is the preferred notation. When we get to 2.2, we'll talk about the definition of the derivative, and this notation is used. So I don't know. Your book gives like 3 different notations, and I don't know why they don't just start with this one and have you practice this notation. I have just posted the theorems for Chapter 2, Chapter 3, and Chapter 4, so I don't necessarily expect anyone to have this. Oops. Where'd that go? Theorems for the book, Chapter 2. Okay, so just kind of recap what we have here. The book gives, like I said, a couple different notations on what they call x, f of x, f naught. So you can see here the slope of the secant line, the slope of the tangent line. If I plug in x naught, I get out f of x naught. And then if I plug in f of x naught plus h, I get out f of x naught plus h. So if I do the change in y over the change in x, I get this part here. In 1.2, we're going to take x naught to be points. Or sorry, in 2.1, we're going to take x naught to be points. 2.2, we're going to take x naught to be x and simplify that. So I'm going to kind of introduce both examples here. So let's look at, let's say I have y equals x squared, and I want to find the equation of the tangent line. Oh, sorry, guys. I have the equation. I want the equation of the tangent line at the point 1, 1. We've done this example before, right? Y equals x squared. We might have done the point minus 2, 4. On Wiley, depending on how many times you did this problem, randomly generated, you might have done the point 1, 1. But we use college algebra to do that. Setting up, okay, let's pretend like we have a slope of a secant line. This point's 1, 1. This point's x comma x squared. Because if I put an x, I get out an x squared. And then we did the change in y over the change in x and factor that out. We're going to do very similar to that. In 2.1, we're going to use the fact that x is 1 in our setup. So if I want to take the limit as h goes to 0 of f of 1 plus h minus f of 1 over h. This is going to give me the slope at x equals 1. So f of 1 plus h, if I plug that into my function, f of 1 plus h would be 1 plus h squared, which would be 1 plus 2h plus h squared. Look, you guys did that one on your quiz, right? It was x plus h instead of 1 plus h. F of 1 would be 1 squared, which would then be 1. So now if I plug this in, I have the limit as h goes to 0 of 1 plus 2h plus h squared minus 1 over h. The minus 1's cancel. Which equals the limit as h goes to 0 of, if I pull out an h, I get 2 plus h over h, which would be 2 plus 0, which would be 2. So it turns out my slope here is 2. Question?
For that, did you just plug in to the left of that?
Here?
Yes. Where did you get all that?
This just came from, this is a setup. Do you understand where this comes from? Yeah. I plug in f of x plus h minus f of x over h. And here x is 1. Okay. And then I just elaborated how I got, if I plug in f of x plus 1, I'm taking f 1 plus h squared. And I get these numbers. Well, let's do the same thing at x equals 2. So y equals x squared. So if I want the equation here, I have y minus 1 equals 2 x minus 1. Because I have a slope and a point, right? Are you guys comfortable with doing that at this point? A slope and a point, you can find the equation of the line. Y minus y1 equals your slope, x minus x1. This is the point x1 comma y1. Is there any questions on that? We'll do more of the equation of the tangent lines as we go, but really the meat and potatoes of this section is the limit, being able to find the slope. Question? So the definition of the slope is this. So I go out here, and if I plug in x equals if I plug in h equals 0, I get 2 plus 0, which is 2. Yeah, that's what we're doing here. This is the slope. This is the slope at x equals 1. So let's look at calculating the slope at x equals 2. So let's look at slope at x equals 2. So I want you guys to calculate that. What is the slope at x equals 2? So what would this setup be? Yeah, the limit as h goes to 0 of f of 2 plus h minus f of 2 over h. Right? So what f of 2 plus h means, everywhere I have an x, I plug in 2 plus h. So 2 plus h squared would be 4 plus 4h plus h squared, right? Minus f of 2. What is it, f of 2? F of 2 is 4 over h. Those 4's cancel, you pull out an h, simplify, plug in h goes to 0, and you get your answer. So let's see the algebra. Keep in mind, you need to keep your limits. So if you have a limit equals algebra, that's not correct. It's a limit equals algebra equals a limit, algebra equals a limit, algebra. So you need to keep those limit signs through your equal signs.
This is 2. If you're plugging 2 in, probably not on this setup. You're squaring, but so you only subtract. So you're subtracting 4.
You're still doing 0.11.
You're doing at x equals 2.
At x.
So it would be 2 comma 4, because you plug in x equals 2 to see what your output would be. If I plug in 1, so here I just gave you the x point, but you should be able to find the y point. Right? At x equals 2 means your point is 2 comma 4. If I plug in 2 to the equation, I get out 4. If I plug in 1 to the equation, I get out 1. In a minute, we'll do an example at x equals 3, which would be 3 comma 9, would be that point. But they might not always give you the point. They might only give you the x value. But to find the y value, you just plug that into the equation. Yeah.
No, that works.
Yeah, but that wouldn't give you any points in this instance. But yeah, it's true. It is. Yeah. So here, so one comment, you would need a limit equals a limit equals a limit. So just some things on notation. There is a faster way to do this.
When we find the slope of the line, like once we got the slope,
Yeah.
do we use the same 1.1?
No, because this slope is at x equals 2.
Then how do we
So what would be your point? If I plug in, my x is 2, what's my y? Well, it's when you plug in 2 to your equation. Your equation's x squared.
Oh, so the to the there's so much stuff here.
Yeah. Good. So you have a point and a slope, so you can write the equation of the tangent line.
So
Good.
our second answer would be the slope at 0.14, right?
Yeah, this is your slope, and this is, it's not 1, 4,
It's 4.1.
2, 4.
Why is it 2.4?
Because your x value is 2, right here,
Oh, I got you. Okay.
right? So if I plug in 2 to my function, I get out 4.
Okay.
So then if I set up my limit, the slope is 4. So you have a point and a slope, you should be able to find an equation of a tangent line, point-slope form. The rest is the same. Okay, so let's look at this one.
Yeah, that's one thing it's wrong.
If I go about doing this, I put equals the limit as h goes to 0. If you do not put the limit, if you do not carry the limit through, you're going to lose points. So you want to make sure you do that. So if I plug in 2 plus h, I end up with 4 plus 4h plus h squared. F of 2 means I plug 2 into my function, which would be 4 over h. So my 4's cancel, equals the limit as h goes to 0. I can pull out an h on top, so I have 4 plus h over h. So my h's cancel here, and I get the limit as h goes to 0 of 4 plus h, which would be 4 plus 0, which would be 4. So this would be the slope. And then the point would be 2 comma 4. So my equation if they asked for the equation, it would be y minus 4 equals 4 times x minus 2. And then you could solve for y there. Right?
Do we need to solve for y, or we just?
Depends on the notation. In Wiley, they're going to say y equals, so you need to solve for y. If they, on a final exam or an exam, if they say find the equation, this is an equation, so it's perfectly fine. Yes?
Okay, I understand, like, I got the 4 and everything with
Mhm.
the slope, and I understand that x equals 2, so that's your x.
Mhm.
How do you know that that 4 is your y?
This is your point on your graph. So if I have my function equals x squared, then if I plug in x equals 2, then y equals 2 squared, which is 4. That's a good question, though. This is all leading to the derivative, which if you've taken calculus before or have taken physics before, a lot of times they talk about the derivative. And it turns out that the slope at any point of this, say, y equals x squared, the slope at any point is going to be a function of x. So let's not call x a point, let's call x x, so we can get this equation or this function. So let's find the slope of x squared at the point x. So if I do that, I have the limit as h goes to 0 of f of x plus h minus f of x over h. This is the difference quotient, right? You guys did that on that quiz. Is everyone kind of following me? Okay, so now I have the limit as h goes to 0. F of x plus h, I take the function, I plug in x plus h, I end up with x squared plus 2xh plus h squared minus x squared over h. So the x squareds on top cancel. If I pull out the limit as h goes to 0, if I pull out an h, I'm left with 2x plus h over h. That cancels. I'm left with 2x plus 0, which would be 2x. This tells me the function for the slope at any point. So if I plug in 1, what's the slope? If I plug in 2, what's the slope? 4. If I plug in 3, what's the slope? 6. So you can see this is beneficial when I want to talk about the slope at multiple points.
But only for y equals x squared.
Only for this function, y equals x squared. This is the definition of the derivative that we will talk about in 2.2. So we will do this in 2.2 more formally. But it's the same setup. Instead of x being a number, x is a variable, a placeholder, right? But you're still going to take f of x plus h minus f of x divided by h as h goes to 0. If x is 5, you can plug that in, calculate it, you're going to get a number. If x is h, you plug that in, calculate it, you get a function. Any questions on that? The problems can get more complicated. You can look at an example like x cubed. And sometimes it's easier to plug in a point. And so that simplifies your calculations versus if you leave x as x. Question?
If you find a point, can you find the rule by somehow figuring out where you started out with?
Eventually we're going to get to power functions, and it turns out finding the derivative is really easy. You're going to, the derivative of x to the 10th is 10x to the 9th. The derivative of x squared is 2x. The derivative of x to the nth is nx to the n minus 1. We're going to prove that, though, so we're not quite there. So there will be ways to kind of prove what's going on there, and then once we learn that, we can apply that to more difficult problems. I'll see you guys tomorrow.